Oops. No. How hard do you want it to be? Oops.
So if we say we don't want it this hard, you'll take it back and change it?
No.
It's a tick mark after Joe.
It's a tick mark for what?
We have 11:30, 1M.
1M, really? Great.
So pizza again?
That was good pizza, too.
What about Wednesday in this class?
Yeah.
I was like, yeah, I didn't get pizza.
Oh, goodness. Keep dipping in my pocketbook, let me tell you. We have taco bar on Tuesday, the next Tuesday, though. It's 3:19. 3:19 for the presentations, yeah.
I was like, you should.
Yeah. Yeah, taco bar, yep. All right. So yeah, you get food. Okay. Oh, shoot. Let me go back to my office real quick. I forgot to bring a sample problem for the one to look at.
So, did you go to the presentations last year?
I did last year.
No,
I did last semester.
Last year they didn't have a slide in their visual thing where they talk about themselves, but I didn't see exactly what they're saying. So I was like,
there was a motivation thing.
I'm just gonna. Yeah, I remember the motivation. I just remember one girl last year. She talked about like how many times she changed her majors,
I can do that.
and stuff like that.
Yeah, you can just leave the motivation to the math part. It's okay.
You don't
I
want to
didn't know
hear
if that
about my
was like
life?
a requirement.
Yeah, you can talk about your life all you want. I'm just saying if you don't want to, you can just leave it to the math part. That's okay. I mean, if the life story is germane to the motivation, that's okay.
Is this one of these problems?
No, this is another problem. We're just going to motivate to get to those problems.
A lot of motivation going on too.
What's that?
Is a lot of motivation?
I know, more motivation going on. All right. So let's say that there is two possible scenarios that can go on for a PDF. And so just made up a discrete PDF here for a couple of different situations. So let's say that X is some random variable that might take on one of these two PDFs. Simplistic view of things, but you already do this kind of stuff when you do hypothesis testing because you know that for the scenarios that we do hypothesis testing on, the PDF changes as the parameter changes. Right? So, I mean, this is a very, very contrived example, a very, very specific idea, but it's still germane to the things that we've been talking about because when you're doing a lot of your hypothesis testing, you're doing it on parameters, you are still changing the PDF as the parameter changes. So it's the same kind of idea. So our hypothesis test that we'll be doing here is how can we tell if we should adopt PDF 1 or PDF 2? By looking at this. I mean, that's all we're doing is just looking. So the whole point of this idea is to start trying to create a critical region to know where you might reject. So what that means is so of course we want to assume that the H naught is the thing that we want to reject if we can, or maybe that's the thing that we think we might want to reject. We want to try to judge whether or not we should reject it based on the value for the X that we get, especially if we're going to do this on a single observation. Say we're going to take one observation for the X, and based on that one observation, we're going to determine whether or not we want to reject the null hypothesis. For our purposes, let's say that by a single observation.
So 0 to 5 are the different PDFs?
Yeah. Yep. On a single observation, we want to determine whether or not to reject the null hypothesis. And just for argument's sake, let's say we want to reject it at the alpha equals 0.1 level. I selected that level. All right, so the idea here is that running through the list of possibilities here, because we know on a single observation the x is going to be something between 0 and 5 here. So the idea is, based on the observation, is it more likely that it came from the HA, the null hypothesis, versus the null hypothesis, the alternative hypothesis versus the null hypothesis, just based on the PDFs here. So for example, if we came across x equals 4, say that was our observation. I'm literally just looking at this piece right here. If it came up with x equals 4, do you think you would reject the null hypothesis? Is it more likely that it came out of the alternative hypothesis than the null hypothesis if the x were equal to 4? Yeah. No, not really, right? Because notice that if we know that the x is equal to 4 ahead of time, it's twice as likely that it came out of the null hypothesis than it came out of the alternative hypothesis, right? So it certainly doesn't make any sense for our rejection region to include 4, right? Because at that point, if the null hypothesis is true, well, we would expect that we would see it twice as likely. So notice I'm even using the terms twice as likely here. So this is the idea. You're trying to get as much bang for your buck. And the idea here is to try to think of a ratio of the ideas. How much more likely is it to get the alternative hypothesis versus the null hypothesis? So let's look at what we call these likelihood ratios. So we've got different likelihood ratios for 0, 1, 2, 3, 4, and 5. So we're going to do the ratio of, I'm going to write it goofy, but I'm going to write it as H naught over HA. I'll use a different notation in a minute, but for right now, all I mean by this is I'm going to take the probability that you got 0 associated with the null hypothesis over the alternative hypothesis. So for the first one, we would get 0.2, right? We'd have 0.01 over 0.05, right? For 1, you would have, looks like 0.5. For 2, you would have 0.75. For 3, you would have 0.25. For 4, you would have 2. And for 5, we would have 33 over 26. That was to make sure everything added up to 1. It wasn't necessarily, it didn't come out nicely, but. And I don't even think it came out to 1 at that point because I think I misadded when I did this. No, I didn't. Never mind. 9, 10, yes, I did misadd. 0.1, I misadded on this. 36, 46. Oh no, 51. That's right. I thought I misadded it. Apparently misadded now. Anyway, those numbers on the end that came out that way because I was trying to get them to add up to 1. Anyway, so again, we're trying to base a critical region off of a single observation. So on that observation, assuming we have the observation, we want to get the most bang for our buck if we're going to put something in our rejection region. What I mean by that is, if I select something to be in the rejection region, I want it to be a lot more likely that it's going to be associated with HA than H naught. Now, the way we've written these ratios, the smaller the ratio, the more likely it was HA, right? So I put the HA on bottom. So which of these gives you the most bang for your buck? Which one would you like to put in the rejection region that gives you the most bang for your buck? 0 does, right? That's at the smallest likelihood ratio. So the first thing we would try is to put 0 in your rejection region. What would be the next one? 3, right? And then I'm just putting them in order. Then we would have 1, then we would have 2, then 5, and then 4 in that order.
So don't we choose the observation beforehand?
What we're trying to do is come up with a critical region, and then we'll get the observation and see if it falls into our rejection region. That's the idea. Based on these possible ratios, that's what we're doing, is we're trying to get the rejection region so that we'll say, oh, if we get this observation, it's in our rejection region, we'll reject. Much like what we've done for other things, right? We get a critical t value or z value or chi-squared value, and then it falls in the region, then we'll say we reject. It's the same concept, it's just on a really, really small scale. Okay. Because our purposes here, we're trying to create the rejection regions from scratch. Okay. All right, so now, remember the alpha is our type 1 error issue probabilities, right? So if we select, let's look at 0 first. If we pick 0, we want to make sure that the probability that we pick 0, given that the actual parameter is that we should have used the first PDF, is less than 0.1, right? That's our significance level. So if we go back up to our PDFs, will I put 0 in my rejection region? Does that satisfy that criterion? If I see 0, is the probability less than 0.1 that I would have H naught? Will I throw 0 in my critical region? Yeah, because this is less than 0.1, right? So far, if I take my critical region, the first number we'll put in there is 0. And again, the reason for that is that the probability of getting 0 and having H not be true is 0.01. Right? That's an unlikely event as far as H naught is concerned, right? Okay. So can we add anything else to our region? Well, we said that 0 had the most bang for our buck in terms of likelihood, right? So now we go to the next one for 3. What's the probability that H naught is true and you get a 3? Yeah, 0.08, right? Now, if I add that to my critical region, do I have a critical region that's still less than 0.1 for probability? Yeah, I do, right? So I can go ahead and add 3 in there.
So, but we added those two together.
We added those two together, right? So
0.01 and
the 0.01, the 0.08. Now, am I going to be able to add anything else? Well, no, because all the rest of them have probabilities that are too big. The next one I would check is 1, right? Because that was the next highest was 1. And at that point, it has a probability of 0.05 happening. That makes my critical region too big, right? I want the probability that you land in the critical region and the null hypothesis is true to be less than 0.1. So I can't add anything else. So this tells us that our critical region has to be 0 to 3, and that's it.
So what is the null hypothesis now? Now that we have
the null hypothesis is that PDF1 is true, and the alternative hypothesis is that PDF2 is true. We're starting this with some very, very simple hypotheses of it's going to be one parameter or it has to be the other. We're not going to have any, it's one parameter and then it has to be bigger or smaller. We'll do that in a little bit. But for right now, we're just like, it is parameter 1 or it is parameter 2. It's one of those two parameters. Okay? All right, so this is how we form that critical region. So if you take a single observation and look and, oh, I got 2, well, then I won't reject. Oh, I got 5, I won't reject. However, if I get 0 or if I get 3, I will reject. Because, again, if you already know ahead of time that I got that observation, it's a lot more likely that the alternative hypothesis is true than the null hypothesis is true. That's how we decided to put those in the rejection region. Does that make sense?
Will always be added up to 1? Like anything less than 1? The end part where you did like the .08 and the .01 and you added those together.
Well, we always want it to be less than whatever the alpha is.
Okay.
Yeah. Now, in certain cases, we'll have our continuous ones. That's where we're headed, yeah. All right. All right, so the process that we just did here is an example of what's referred to as the Neiman-Pearson lemma. So the Neiman-Pearson lemma goes along with what's referred to as best critical regions. So I'll get to the lemma here in a second, but let's do a definition. Let's consider just a very, very simple hypothesis test. All right, so we've got a hypothesis test that says a parameter theta can take on one of two values. The null hypothesis is theta equals theta naught. The alternative is theta equals theta 1. We're going to let C be a critical region of size alpha. So again, of course, what this means that the alpha is the probability that you land in the rejection region given that the null hypothesis is true. That's exactly how we did our alphas for all of our hypothesis tests, right? When you found the critical value, you found your critical region. It's the probability that you're actually in the rejection region, but you shouldn't have been, right? That's the type 1 error idea. Okay? Then we say C is a best critical region of size alpha if for any other critical region D of size alpha we have that the probability of C equaling theta or given theta 1 is greater than or equal to the probability that D given theta 1. All right, let's think about what this means. Before I write it down in words, let's think about what it means. My alpha, I have the same size rejection region for C as I do for D, in terms of alpha, right? So I say this, it's the same probability that you land in the rejection region if the null hypothesis is true. So they have the same probability of a type 1 error. But what's the second piece of this computing? This is you land in the rejection region given that the alternative hypothesis is actually true. That's power, right? This is power, isn't it? Okay. So this idea of best critical region of size alpha is saying that I have a whole bunch of possibilities for regions that might have size alpha. I want to try to find the best one that, and by best we mean most powerful. The one we'll actually reject when we should. Okay? So this says that, in other words, the power associated with C is greater, or at least as good, greater than or equal to the power of any other critical region of size alpha.
So we're trying to minimize beta while keeping alpha constant.
Correct. That's exactly right. We're trying to minimize the beta while keeping the alpha constant. That's exactly right. What we're headed to is the idea of what's referred to as the uniformly most powerful region. So we're headed towards. All right. They give a proof in the book. The proof's more symbols than anything. It's not that bad. I'm sorry, not a proof of this. This is a proof of the Neiman-Pearson line. I'm sorry, I jumped ahead of myself. I just did a definition. There's not a proof of a definition. It is the definition. All right. So now the idea for the lemma. All right. So let's talk about what the lemma means. So we're going to take a random sample, and we're going to have our likelihood function idea here again. So let's let the likelihood of theta denote the likelihood, of course, of theta given a random sample. We've had this notation before in lots of contexts. Since it's a random sample, that just, of course, means that we're taking the product of our PDFs if there exists a constant k, and it has to be a positive constant, of course, because I'm going to be talking about probabilities, so it better be a positive constant k, and a subset C of the sample space, such that the following three criteria are met. I know it's a lot of words. We'll see what happens as we go through the problems. A, the probability that your random sample lands in your critical region given theta naught is equal to alpha. The likelihood of theta naught divided by the likelihood of theta 1 is less than or equal to k for x1, x2, xn in the critical region, and the likelihood of theta naught over the likelihood of theta 1 is greater than or equal to k for x1, x2, out to xn in the complement of C. Okay, lots and lots of words, I know. We're going to get to an example to see what we mean. The conclusion is then C is a best critical region of size alpha for testing the null theta equals theta naught against the alternative theta equals theta 1. We did this in the I know there's a lot of words, and like I said, the words will be more helpful when we get to some other examples that actually go through some specific types of distributions. But let's think about to the previous example of what we did. Okay? We computed all of those likelihood ratios. Right? We knew we wanted a critical region of size alpha. So what did we do? We ordered up our likelihood ratios from smallest to biggest and started sticking things into the critical region until we hit alpha. I mean, we didn't quite hit alpha, but we got as close as we could to alpha because it was discrete, right? Notice that your k is some constant that's going to depend on what your alpha is and what your PDF is. We're not exceptionally interested in k. Okay? What we're interested in, of course, is finding the C with respect to the alpha. Our goal, though, of course, is to try to get this likelihood ratio bounded by some constant. That's the idea. Okay? Now, the constant itself doesn't necessarily, the K doesn't necessarily matter. It'll be instrumental in figuring out what the critical region is, but it's actually what the value of K isn't all that exciting. Okay? Now, things associated with it will be. What was our K value, or at least what could we use for our K value? Well, let's think about what our ratios were. Our first one was 0.2, the next one was 0.25, and the next one was 0.5, right? So we could use 0.25 for our K, right? Because we stuck the two things in the critical region, that the likelihood of theta naught over theta 1 was less than or equal to 0.25 when they were in the critical region, and it was greater than 0.25 when it was outside the critical region. And our critical region had the right size. So in that previous example, we found a best critical region for the hypothesis test of H0 versus HA. That's what we did in that example. Okay? We just followed this idea for the lemma. Okay? So let's see if we can do this in terms of specific example here. So let's look at, this is 10.3.1 on page 518. We're taking a random sample from a normal distribution, unknown mean, but the variance is 64. We want to show, part A asks us to show that C equals, we can actually express our critical region in terms of the mean being less than or equal to some constant is a best critical region for testing mu equals 80 against mu equals 76. So again, we're starting these off by doing very simple hypotheses, right? There's only two possibilities for the parameter to equal a value. Well, again, we're going to build up from here, but we start off with just these two possibilities. Okay? All right, so here's the process that you want to go through. We want to compute this ratio of likelihood functions. So theta naught, of course, is referring to the parameter with respect to H naught. And theta 1 is referring to the parameter with respect to HA. Okay. Remember, our likelihood function is the product of the PDF with each of the points of the PDF with itself, with each of the random sample pieces plugged in, right? So we've got product I equals 1 to n. We've got a normal distribution, so our PDF is going to look like 1 over 8 times the square root of 2 pi e to the net minus x minus 80, or x of I minus 80 over 2 sigma squared, so 160, or excuse me, 128. It's going to turn out those values aren't going to be very important. All I did was take the PDF or the normal distribution. We're given that the variance is 8, or excuse me, the variance is 64 regardless, so sigma is 8. So I just plug those into the PDFs. All right. We're going to work backward. According to the Neiman-Pearson lemma, to find a best critical region, I need this to be less than or equal to some constant, right? Now notice we already trying to, we already know what we want to show. We want to show this, right? So I want to show that, or basically what we want to do is we want to take this inequality and work down to the point where we see mean is less than a constant. Doesn't matter what the constant is, I just need to get to mean is less than a constant. We'll worry about what the constant is here in a minute. That make sense? Okay. All right. Well, this is a product of a bunch of crap. There's quotient of a bunch of product of a bunch of crap. I want to get this, and I want to talk about means. I want sums. How do I change products to sums? Yeah, take a log, right? So let's log both sides. All right. Logs turns things in from products to sums. So when I log this, it'll change all of this into a sum. Also notice, I should have noticed this to start with, so I don't have to rewrite it. Notice that this is on top and this is on bottom. I could have gone ahead and canceled these to start with. All right, so I'm just going to do it. Because I could have just factored out that constant to the nth power on top and bottom, so I don't have to rewrite it. So here, I get log of a product becomes the sum of the logs. The log cancels the e, right? And when I would have taken the product, I would have added these things together. So the top just becomes the sum of negative xi minus 80. Oops, these are squareds. I forgot squareds on my exponents here. Over 128. And then I'll have minus a minus. It'll be plus the sum from I equals 1 to n of x sub I minus 76 squared over 128. Now, the 128s are constants. I can pull them out in front of the sums, and I can shoot it across to the other side, right? So I'll have negative the sum I equals 1 to n, xi minus 80 squared, plus the sum I equals 1 to n of xi minus 76 squared is less than or equal to 128 log k. Again, could not care much less about the right-hand side. All right, let's say if I FOIL this out, notice that you'll get a sum of x sub I squared in the first term, and it'll be negative. You've also got a sum of x sub I in the second term, but it'll be positive. So the sum of x sub I squareds will cancel, right? Here I'll get positive 160 x sub I, right? Here I'll get negative 152 x sub I. So you're going to get 8 sum of x sub i's. And I'm going to stop writing the index because it's redundant. And then I'll get negative sum of 80 squareds. So you'll get negative, what is that, 6400n. And then this one will be positive, what's 76 squared? I'm just going to write it as 76 squared n. I don't feel like doing it. Well, it's 4900 plus 840 plus 36, whatever that is. I don't really care. Here's why I don't care. I'm going to move this. This is just a constant. I'm going to move it to the other side. Still just a constant, right? Right? And then now I've got 8 times the sum of x sub I. But I can move the 8 over to the other side and divide by n. So I'm going to get the sum of x sub I over n is less than or equal to some constant. That's all I really cared about. Which is the form we wanted, right? It said, show that the critical region can be described by x bar is less than c. Here's x bar is less than or equal to some c.
Oh, so is the lemma all the three statements are equivalent? That is, if one is true, the other two are. Because we assume that that would be bounded.
We're working basically backward. If I can find this constant c, I can work backward and get my k.
Oh, okay.
Yeah. And then the complement will also have to be true. So we're basically working backward at this point. All right, so the second part gets us actually some honest to goodness numbers. The second part here says find n and c so that our alpha and our beta are approximately 0.05. All right, so remember that alpha is the probability that you're in the rejection region. So in this case, x bar is less than or equal to c, given theta naught is the parameter. So this will be given mu is equal to 80. Right? Beta is the probability that you are not in the rejection region when you should be. Right? Those are the values of alpha and beta, aren't they? Alpha is we rejected, we shouldn't. Beta is we didn't reject, we should. Right? Do you agree? We want these both to be 0.05. Now, what kind of distribution does x bar have? Normal. So if the probability is going to be 0.05, we know what the z-score for x bar should be, right? Or what the z-score for that c should be. For this first one, we would need c minus 80 over 8 divided by the square root of n to equal negative 1.645. Right? The 1.645 is the probability of the z-score associated with 0.05. So I need this z-score, and the z-score is going to be data point minus the mean over the standard deviation. And this part's central limit theorem here, right? We agree? That part's the central limit theorem part. Okay. Over here, it's written a little differently, but I want the probability where I'm greater than c to be 0.05. That's going to be still 1.645. It's just on the right tail, right? So I want c minus 76 over 8 over the square root of n to be equal to 1.645. Now I have two equations and two unknowns. It's not that hard to solve. C minus 80 equals negative 1.645 times 8 over the square root of n. C minus 76 is equal to 1.645 times 8 over the square root of n. This is C minus 76 minus 4, right? So I can do 1.645 times 8 over the square root of n minus 4 is negative 1.645 times 8 over the square root of n. Rearrange this. 4 square root of n is 16 times 1.645. Just doing algebra quickly, but I'm just doing algebra without doing arithmetic because I didn't want to do that. So I would divide by 4 and square both sides. So your n should be 4 times 1.645 squared, which is about 43 if I remember correctly. You can check it, but if I remember correctly, it should be about 43. Actually, the answer's in the back of the book. I can tell you. Yeah, it's about 43. And if you plug that n value in for one of your equations, you can figure out c. So your c will be about 78. Actually, if you use the exact value for n, your c will be exactly 78. So notice what we're doing. We're picking our significance level, figuring out what the critical region has to be, and also trying to control the power at the same time, making sure that your power is at least 90.95. This is how you use the likelihood idea. We'll see if we can do another one.
In the A part of this question, why didn't we have to show that that the probability of x bar is smaller than c given mu is equal to alpha? I wouldn't even talk about alpha.
We hadn't picked the alpha yet.
So we can't do this dilemma. We can use this without even picking alpha in the first place.
If we know that we could, if we know that it makes sense to pick a critical region like that, yeah. So, because once we pick the alpha, we know that we can figure out what the x bar has to be. The important part is that we were able to use that positive constant k to do it. Yeah. And we will always get a positive constant in that case as long as we pick an appropriate, well, in that case, it'll always be fine because your means could be anything. They could be negative infinity to infinity, so we don't have to worry about anything there. The only place where you get a little bit tricky is if you have to worry about that. If you worked backwards, your k could be negative. Because remember, we took a log to start with, which would be a problem. That's the only thing we really have to worry about, which is kind of cool. All right, let's look at the exercise 11.41. So it should be on the back side, I think, of the first page of the handout that I gave you. This was a little bit more straightforward, I think. Stop that yawning.
I freaking hate it. It's so bad this morning. I don't know why. I fell asleep at like 9 p.m. last night.
All right, so your null hypothesis is lambda is 1. Your alternative hypothesis is lambda is 2. We're going to use a single observation from a Poisson. Okay. That makes life a little bit easier because we don't have the whole product of a mess, right? Okay, so again, we still want to use the Pearson, the Neiman-Pearson lemma. Okay, so let's calculate our likelihood ratio. So in this case, our parameter is lambda, and we're checking it of 1 versus 2, right? We're doing a single observation, and it's a Poisson distribution. So the top likelihood is just going to be e to the negative 1. Right? Our bottom likelihood is just going to be 2 to the x. Over x factorial. I forgot about the x factorial part. And then 2 to the x, e to the minus 2 over x factorial. There's a 1 to the x that's just 1, right? And we want this less than or equal to k. Again, the k doesn't really matter. We just are assuming it's some positive. We want it to be a positive constant. That's the important part. So far, so good? All right. X factorials will cancel. I've got e to the negative 1 over e to the negative 2. That just gives me an e, doesn't it? My e to the negative 1 over e to the negative 2 is just going to give me an e. I can move that to the other side, so you get 1 over 2 to the x is less than or equal to k over e. 2 to the x is greater than or equal to e over k. So x will be greater than or equal to what? 1, it wouldn't matter. I'll write it as natural log of e over k divided by natural log of 2. Doesn't really matter.
Just say natural That's log of 2.
Say again.
Let me just think that's log of 2.
All right. So again, this is just a constant, right? That's all we really care about. This is a constant. So the form of your, what this tells us is that the form of our rejection region is the set of all x such that x is greater than or equal to some constant, some c. That c is going to be based on the significance level. We want the probability of c happening given lambda equals 1 is equal to 0.1 in this case. Now, it's a discrete distribution, so the chances that you're actually going to get it equal to 0.1 is pretty small. Okay? There's not a lot better way to do this besides brute force it. Okay? The probability that x is greater than or equal to c needs to be 0.1 or less than 0.1. Okay? If you do the probability that x is equal to 0 in this case, you get e to the negative 1. If you do the probability that x is equal to 1, you get e to the negative 1 as well. If you do the probability that x is equal to 2, you get e to the negative 1 over 2. Then your lambda is 1, so you don't have that lambda to the x piece in there, because it's 1 every single time. If you add the three things of these together, you get 5 halves e to the minus 1. Hopefully there's a, is there an e on here? Yes, there is. So negative 1 e to that power times 5 divided by 2. This is about 0.9197. So notice that I've computed basically the complement of this, right? So what does your C need to be here? It needs to be 3, right? Because this is the complement. The 0, 1, and 2 are complement. So this needs to be at least 3. Because if it's 2, you won't have the right value. 2e to the minus 1 is about 0.7358. It's too small. Okay. So C has to be 3. All right. So we want the power. This is the probability that x will be at least 3 given that lambda is equal to 2. Power is you made the right decision, right? You rejected when you were supposed to. That's power, right? So this will be 1 minus e to the negative 2 minus 2e to the negative 2 minus 2e to the negative 2. This is x equal to 0. This is x equal to 1. This is x equal, I'm going fast because I'm out of time. That's using lambda is equal to 2. So you get, what is that, 5e to the negative 2. So you get about 0.3233. So it's B is your answer. Not very powerful. Which is not a huge surprise because you're trying to reject a null hypothesis using a single observation. I mean, in general, the only way that you can make your power higher is to increase your sample size. So if you're using a single observation, you shouldn't expect a very powerful test.
Does this lemma extend to the kind of hypothesis test we actually do in a little time?
Mm-hmm. Yep. Yep. So we'll do more of these examples next time.
Interesting.
you have a question?
Yeah. Wouldn't, like, when you do, so, like, when you get to the x equals 2, wouldn't it be 2 squared e to the, well, that one would be
2 to the negative 2 squared e to the negative 2 over 2 factorial.
5.
So 2 squared over 2 is 2. Yeah, that's what it was. Yep. I said, like I said, I was making it quickly because once I'd already done the problem ahead of time, so I knew it was supposed to be. That also helps.
Yeah.
Also helps that I made a mistake the first time I did it and had to redo it. So. I never make errors.
Never.
Never.